So, Dylan Martello, are you there?
Yes, I'm here.
Hey, awesome. Welcome. Welcome.
Oh,
Okay, so while you bring up your slides, I'll give you your little intro
okay.
and
Awesome.
and then we'll run with it. So, Dylan Martello of the Stephen Winters Associates is presenting today on electrification of domestic hot water. By the way, I just want to acknowledge that they're real leaders in cold climate domestic hot water heat pumps for years, and I've gotten to see their presentations. So Dylan Martello is part of the Passive House team at Stephen Winters Associates. SWA takes targeted approaches to serve the individual needs of each client and project. They work across teams to create holistic solutions to the challenges facing our buildings and communities. They pride themselves on having a shared value of fostering camaraderie and the desire to improve the built environment. Welcome, Dylan.
Thank you. Thank you. All right. I am just getting situated here on my slides. So let me share my screen. All right. I'm going to do the screen here. Okay. Can you guys see my screen?
See the screen, still the slides off to the left. So I haven't got. Oh, now we've got the notes on the right-hand side and such.
So I switch this.
I do the lower right-hand one where it's got that's the one, my favorite button.
Okay.
Oh, that's not the one though.
I don't know why. Hold on one second. Let me switch my monitor. I have the second monitor and I think that's what's causing all the problems.
No worries.
Just take this out. Actually, I don't even need my second. All right. Okay. Cool. You guys can see my screen? All right.
Perfect. Off you go.
Sweet. All right. So thanks for the introduction. My name is Dylan Martello, and I'm glad to be here with you guys today. I'm going to talk about electrification of domestic hot water. And I'm going to try to pack a lot in a short amount of time, but I want to make sure I have enough time for getting through some of the case studies and some real world applications of this stuff, because that's the exciting times that we are in. And I want to make sure I have a chance to talk to that. So if I feel like I'm rushing at any point, I will try to slow down, but and I'll give you my contact information at the end. So if you have any questions, pointed things to ask, let me know, reach out, and I can clarify anything as needed. But yeah, as Sean mentioned, Stephen Winters Associates, we are a building design consulting firm and construction consulting as well. We work on all things from all green building certifications like LEED, WELL, Passive House, which is my forte. We do general sustainability consultant, decarbonization, and accessibility consultant, enclosure support. So we kind of run the gamut, and we see a lot of projects through early design all the way to construction, and even after construction in this commissioning and operational phase. And we have a lot of good lessons learned from both the early days of projects and the later days of projects to sort of put it all together and see what we can do to make buildings better and make them sort of perform better. So just a quick outline. I want to just briefly mention just some high level things that have been in the news or in the laws really around electrification, and in particular about domestic hot water. Then I really want to dive into a big decision point for domestic hot water design is whether or not a project goes with central or decentralized system. And the electrification implications really depend on that decision. So I want to kind of hone in on what those decision points are, how they're usually made, and how they could impact our designs. Then I'm going to talk about centralized domestic hot water electric options. And then I'm going to talk a little bit about decentralized domestic hot water options, and get into sort of the how we can do this and what sort of schemes are out there and what works and what doesn't work and all that sort of stuff. And then talk a little bit about, which I don't actually have in this outline, but I'm going to sort of talk a little bit about semi-decentralized systems or semi-centralized systems, and kind of talk about their benefits. And then, as I mentioned before, we're going to get into some case studies. So let's start with in the news, in the laws. So a lot of you may have heard, I'm from the Northeast. I live in Connecticut, just outside of New York City. So we do a lot of work in New York City and Massachusetts. So we the first two on here are things that are very close to home from my work. And the first one is the new law, the electrification law passed in New York City. And in short, there's a lot to this law, and there's definitely some exemptions around commercial kitchens and emergency use and labs and things like that. But really, at the end of the day, as it relates to domestic hot water, buildings that are less than 7 stories must have electric domestic hot water by the end of 2023, at the end of next year. So it's really, really a short time frame, but now is the time that we have to address these issues. So now, for buildings that are greater than 7 stories or 7 stories, they get a little bit more of a leeway on this timing. So they must have electric domestic hot water by the end of 2027. And this is all at the time of permit filing. So there's really a tight timeline on these buildings, and really, a few years from now, where these buildings that are 7 stories or greater, which those tend to be the more challenging ones to electrify. That's not a lot of time, given that a lot of these larger buildings take sometimes 5 years, if not longer, to actually develop, design, and construct. So this is it's a very aggressive timeline. Boston City Council has also voted to ban fossil fuels in large buildings by 2050. There's a lot of energy stretch code development going on in Boston, and they're really a leader in terms of pushing the envelope from energy efficiency standpoint. But there is a push to fully electrify buildings and ban fossil fuels in large buildings, which is a big step by 2050. But we'll probably see movement on that even prior to that. And then the city of Denver has also passed an all-electric, or council has voted to pass an all-electric law for large office and multifamily buildings by 2030. So we're really seeing a big push. And the big thing here is really how this all relates to buildings that have high hot water loads. So we're really going to be talking in the lens of multifamily and hotel applications here. So central or decentral or semi-central, which do we choose? What are our decision points? What kind of plays into this? So from what I've seen, really a lot of common decision points here are one, very often it's what are we used to? What have we done in the past? A lot of times developers, owners, building designers even sometimes don't really feel very comfortable changing from a systems sort of architecture that they are used to using. So if decentralized has been used in the past, that's probably what they're going to want to go with in the future projects. Another aspect to this, and it's a really, really huge point, is metering, and whether or not the building owner pays for hot water or they want that cost paid to the tenant. So there are some nuances to that I'll get into in a minute. Some other decision points here are, do we have space for these sorts of things? So common questions here are, do we have space for a boiler room or a domestic hot water room in our building, let's say on the roof or in a cellar? And that's really with a centralized system. When we have a decentralized system, do we have space for water heater closets and adequate free air volume that these water heaters actually need? So we need to actually make sure that they have space around them and have airflow available to them in every single apartment, when rentable square footage is such a premium in many markets in this country and around the world, really. This is a huge question. And then, in the lens of a potential semi-centralized system, or let's say like a floor-by-floor system, do we have space for a small little domestic hot water or a boiler room on each floor? There's a lot of pros in terms of efficiency and aspects of the design that are really beneficial by doing a semi-central system. However, you're eating into potentially one apartment on every floor, which that has huge implications. So there's a lot of big questions there around just, do we have space? Another big question here is, if and this is a question that's been asked a lot, especially 3 or 4 years from now, or 3 or 4 years prior to now, is really, do we have the ability to future-proof this design now if we aren't installing an electric system now, when we ultimately will need to convert to electric systems, let's say in 10, 20, 30 years from now, are we quote unquote future-proofed to do this? So really this is, think about it from a central system perspective, it's a lot easier to replace and sort of retrofit one central system in most cases than going into every single apartment, ripping into the walls or ripping in a mechanical closet and changing the gas system to an electric system. So this is kind of a huge point too in a lot of projects. And then lastly, do we have enough structural capacity, let's say for a boiler room or domestic hot water room and storage tanks on a roof? And that's a very legitimate question and needs to be factored into the planning. So just as a sort of summary here and very, very high level, there's a lot to these decisions about central, decentral, or semi-central. But when we look at a central system, one of the biggest challenges here is how metering is addressed. In many cases, the building owner will just pay for the domestic hot water in this type of system architecture. If they wanted to pass the cost on to the tenants, they would have to pay for twice as many meters because you need a meter on the hot water side as well as the cold water side. And you also have to maintain those meters. So there's really a big cost just to pass that cost, the operational cost, onto the tenants. However, with the central system, there's a lot of different design approach options. And as counterintuitive as this may seem, there's actually a lot of flexibility in the systems that are out there and how they could integrate with the other systems in the building that we'll get to in a second. And as I mentioned before, central tends to be a more future-proofable system from what we've seen. But when we look at decentralized systems, the tenants, generally speaking, this is when the tenants would pay for the hot water. And this really could potentially lead to less water usage. I think there's certainly a valid case that people that have to pay for their own hot water will use less hot water. So in terms of just reducing the usage of water, this is actually a kind of a important point that I think is worth bringing up here. And then lastly, with the decentralized systems, tenants have the ability in many cases to operate the water heaters. And as I'll mention a little bit later, this can either be a good thing or a bad thing. So we've seen sort of bad versions of this where heat pump water heaters have been just changed in terms of how they operate. And but sometimes that controllability is desirable amongst tenants as well. And then with the semi-centralized system, I think one real benefit here, and there's a lot of efficiencies to it, despite the cons in terms of the space it eats up on every floor. There's a potential that it could open the door for more mid-size water heater options that tend to be a little bit more tried and true than the large commercial scale central system. So a semi-centralized system might offer a little bit more comfort in terms of what system is selected to provide the hot water. Okay, so centralized system, let's dig into this. So these are just sort of Fred Flintstone style sketches, one-line diagrams, whatever you want to call it, of just the different options. And I tried to sort of label these so we can summarize and see these at the end of the presentation. But the first option here is really when we have an air source heat pump. It's a centralized air source heat pump. It's located outside, typically on the roof is what we've seen. So you have to sort of factor that in when you look at the structural capacity of the roof and other MEP equipment on that roof. And then you have a refrigerant loop, which, the exciting thing is now we're seeing a lot of systems that use CO2 as a refrigerant, which has a global warming potential of a whopping 1, or if refrigerant leaks, it's only going to emit the same amount of CO2 equivalents of leakage. So that's sort of compared to more conventional refrigerant like R410A or 134, where you're losing thousands of CO2 equivalents for every 1 unit of refrigerant gas released into the atmosphere. So CO2 refrigerant has a lot of other benefits as well, but it's just a very exciting new technology that we're seeing implemented now. Then it typically will go through a heat exchanger where it will essentially transfer that heat from the refrigerant loop into the hot water storage system, and then ultimately to typically a recirculation loop for domestic hot water to the apartment. Now, big challenge with this, and this is a big part of this presentation is, and part of presenting case studies is really how is this applied in cold climates? That's really the big question. In climates like Southern California, we have developers that we work with that have buildings in Southern California that are multifamily and are using air source heat pumps, but the climate is much more mild. So there's really no concern for one, will the units operate in low temperatures, and will we have enough capacity to provide hot water to the building in the winter time? So that's really the key question here. Now, when we talk about an alternative approach here, which I'm calling option C2, this is really a water source system approach. And this first sort of system architecture here is really for a retrofit application. So this is where you have an existing building that maybe doesn't have any roof space available, which is, this is the one benefit of this system, but you have some interior space to work with. And they have an existing boiler plant. So this is just sort of we're referencing this design in the heating season in particular. Now, what we can do is we can add a water-to-water heat pump and have that water-to-water heat pump essentially steal some hot water off of the existing boiler plant's loop that's providing space heating hot water to the building, and convert that water to even hotter water that goes into the domestic hot water storage system and ultimately to the building. Now, as I mentioned before, we're sort of stealing heat from that space heating loop. So it could impact the efficiency of the heating system a little bit, or the boiler plant might need to work a little bit harder to make up for that. But in the long run, you're still getting some efficiency gains by providing all of your domestic hot water via a heat pump based system. And the other benefit to this is that you don't need to worry about cold climate performance, because this boiler plant will be operating at a uniform temperature throughout the year and throughout the heating season. Now, in the cooling season, here's where this gets really interesting and really awesome, is because the water-to-water heat pump will actually, as a result of making hot water, will reject cold water. So just like where you have like an integrated tank heat pump water heater that in order to make hot water, it's rejecting cold air. But when you have a water-to-water heat pump, it's actually rejecting cold water. So what we can do in a retrofit application is when we have this water-to-water heat pump, when we tie it into the cold water supply for the building for space cooling, we actually see sort of a nice synergy here where by producing domestic hot water, we're almost utilizing a pretty large amount of heat recovery essentially to get free cooling injected into that cooling loop. So in the cooling season is where we really see a nice benefit with having this water-to-water heat pump. So when we look at this same style system, now we need to think about, okay, but what happens when we electrify the existing boiler plant and electrify the existing systems? Because we need to electrify everything ultimately. We can't just electrify the domestic hot water end use. So this is where we get into option C3, which is very similar in that you have your water-to-water heat pump located indoors, but now you can integrate an air-to-water heat pump that's located outside and providing heat via heat exchanger to what we call like a mild temperature water loop. And this is really interesting because what we're seeing is that you can utilize this air-to-water heat pump to provide water that's anywhere between, let's say, 70 degrees to 100 degrees Fahrenheit year round. And that water is circulated to the building in the existing hydronic piping, or if it's a new building, we can use the new piping. And that goes to the apartments for either space heating or space cooling. And you can utilize water source heat pumps in the apartments. You can utilize fan coils in many cases. There's different aspects of the design that need to be factored in, but there's a few options on the terminal unit strategy. But this temperature or this water loop runs at a fairly mild temperature year round. And what we're doing is kind of like I was describing before, we're almost stealing heat from that water temperature loop or mild temperature water loop. That water-to-water heat pump is going to take some heat from there and inject it into the storage system. And then, as a result of that, it will inject cold water or colder water back into this mild temp water loop. So we're still seeing the benefit in the cooling season of that heat recovery. But in the heating season, we're stealing that heat. So now that needs to be sort of offset. And that's what the air-to-water heat pump is here to do. It's here to sort of just kind of temper that water loop so it keeps it in that sweet spot year round. So this is a very, very interesting design approach. and is one that I think is sort of where we can take our existing hydronic buildings to ultimately in an electrified manner. The last option here for Central that I wanted to talk about was where we have a water source-based system with a geothermal loop or geothermal wells. So this is where we're using either water, and we can use open wells or closed cells, or closed wells, closed systems, and that will dictate what the solution is. So it's either going to be water or glycol, and that will run into a water-to-water heat pump that is basically using that heat from the ground to make hot water. And that's a fairly simplified version of this, but it can work. And when the sort of soil characteristics and ground characteristics are good for this, then it can really make a lot of sense. Okay, so some decentralized options here. Now, the first option I want to talk about is a fairly maybe contentious topic, but it is one that I think is worth mentioning here, and that's electric resistance tanks. So this is certainly not new technology. We do see it a lot in many cases. However, the real downside to this is that it doesn't really have a coefficient of performance or efficiency. Its efficiency is just 1, essentially. You'll lose some heat through the tank, so you want to make sure those tanks are insulated. But in terms of the electric resistance tanks, it's going to be a little bit more costly. Well, it could be a lot more costly than gas systems if tenants are used to gas sort of fired hot water systems. But it is an electric-based system. It's going to use a little bit more energy for sure. But there are some pros to it in that it is electrified, and if you can offset that with renewable energy, it's one of the simplest systems to design. And in many cases, sometimes simple is honestly the best system, because there's very much the potential for more complicated systems to just be harder to maintain, harder to operate well. So I think this is worth mentioning here, and we do see some cases where it actually makes a lot of sense to go down this route. Now, the alternative to this would be to utilize either heat pump water heaters that are sort of sourcing its air for heating from the apartment, or in the next scenario that we'll see here in a second, sourcing that air from corridors, which is a sort of innovative strategy. But just thinking about the heat pump water heater located in the apartment, sourcing its air from the apartment. Now, the thing to keep in mind with this is these heat pump water heaters need to have at least 1,000 cubic feet of air volume available to them in order to operate properly and not freeze out the space they're in. So, you can't just tuck it in a closet and forget about it. You have to really think about how it's operating, how much air it's getting either through louvered doors or through a ducted system, or where it's getting that air. The other thing is that these reject cold air, and if they're just ducted back into an apartment, you might get some comfort complaints, especially in the wintertime. Lastly, these heat pump water heaters have compressors in them. Those compressors are noisy, and they're located in an apartment. So we've actually measured apartments where these compressors are running, and the decibel levels are, we're seeing that they're loud, and in addition to hearing from tenants that they're just noisy and, getting complaints about that. So there's some, I think, very legitimate concerns to this system. It can be done right. It's just there are design challenges that need to be really thought out and really ensure that these are being addressed, because ultimately what we're seeing when these design challenges aren't addressed properly and the tenants have control over them, we are seeing tenants go in and either switch these units to electric resistance mode, or make complaints to the building operators that then come in and switch these units to electric resistance mode. So we have to be really careful, because if we just go gung-ho about heat pump water heaters in apartments and don't think about designing them properly, we're going to just end up installing electric resistance everywhere. And that's something we don't want to happen, especially when we're investing all of this money in this heat pump technology. We want to actually use it. So that's something that we really just got to be careful with. But that's where this leads to, I think, a very innovative approach, which is to essentially duct the cold air or reject the cold air from the heat pump water heater to the corridors. Now, one benefit to this is that it would still be located in a closet that's adjacent to the corridor, and it will inevitably be adjacent to the apartment. However, we now have a lot less penetrations through those walls, and we don't really need a door to that closet from the apartment. We can have access provided via an access panel in the corridors. So what that means is that we can now focus on sound insulation, particularly in that closet, a lot more closely at the apartment walls. So we can try to isolate the noise of these units a little bit better. We're also rejecting air into, move these slides. We're also rejecting air into the corridors now, not the apartments. So if these units are running and rejecting cold air, it's not going to really be felt by the tenants. It's just going to be felt in corridors. But in my opinion, it's either winter and people are wearing jackets walking through a corridor, or it's summer times and people like feeling cold in the corridor. So I think there's like a lot of positives to doing this, to rejecting the cold air into the corridors. And then lastly, they can be maintained from the corridor. So you don't have to get in the apartments. You can access them from a common area, which is a very desirable thing. You just got to be careful that you have adequate heating capacity though in the corridors. So you don't want to like freeze the corridors out, right? You want to make sure that those heating systems have the ability to heat that air. But like I said, there's really, I think, a lot of upsides to this potential approach.
Oh, and Decina, you are at time, so you might want to do a little wrap up.
Okay, all right, sounds good. I will try to speed through here in like 2 more minutes. So semi-centralized systems, in short, there's a couple different options. You either go floor by floor, or you go top down where you're all on the roof, or you go bottom up where you're sort of in a garage or at the ground level. And these are sort of the summaries of the options here. So really quick, because I know a lot of people are interested in this, just case studies of actual applications of this technology. Centralized Systems, our company, we are working on 5 projects total right now that are utilizing air source heat pumps. 2 have recently been operational. 1 is in commissioning and 2 are in late design. And then we have 1 that's in late design that's actually a water source heat pump tied to an existing hydronic plant. And then on the decentralized side, we have obviously many projects that use electric resistance tanks. We have a handful of projects using integrated tank heat pump water heaters, which is where we learn a lot of these lessons. And then lastly, we have 1 project that's in very early design that might do this ducting the air to corridors option. So, and then we don't have any semi-centralized systems. So I won't talk about all these projects in whole here, but I'll just quickly give you guys some points of reference. So that way, if you want to reach out to me, I'd be happy to give you a little bit more information. But Hotel Marcel, it's a project in New Haven, Connecticut, using the centralized air source heat pump Mitsubishi units. That should be in operation this year, so that's exciting. Rubin Hall, which will be construction will be started this year. It's a renovation. Sorry for not having the units in here, but it's over 100 apartment style dorms. But they're utilizing a Colmac water to water heat pump, which is a very, very cool technology, and air source heat pumps for heating. Sandon, we have a lot of pilot project where we're using Sandon CO2 refrigerant heat pump water heaters that's displacing some existing fossil fuel based domestic hot water generation. It's recently operational. 60 units in this building, and we're starting to get some exciting data back on that. And then we have a couple of big projects using an air source heat pump water heater, the Link by Watts Aegis A unit, with construction anticipated to start next year. So these are huge buildings using centralized systems. And then our Northland Newton project is using electric resistance tanks with PV ready roofs. And the big takeaway there was metering was the big decision maker, and the concerns with heat pump water heaters in the apartments was a big factor. We had to take that into account. And then lastly here, this is a project that is not a SWA project, but I want to include this in here and give a shout out to Tatum Engineering, who just presented on this project in upstate New York in Ithaca. It's 124 units, and they are operational, and they're using the Sandon Sanco CO2 heat pump water heaters in sort of a plant style with electric resistance backup. And they are actually seeing in the first few months of getting data back that the system's actually working very well. So we're seeing some positive results of projects now in operation. So this is really exciting times. All right, sorry for speaking really fast. I'm from the East Coast, so I'm used to talking very fast and I sometimes get yelled out about it, but it's a huge topic and I really wanted to thank you guys for listening in, and please reach out if you got any questions.
That was a fabulous technical review with great case studies and lots of good advice.
Yeah.
Well done, especially working in such a cold environment. I mean, in California, you frequently see water heaters put out in patio closets because the freezing is not a real issue.
Yeah.
So I appreciate you having to no, that's a constraint.
Absolutely. Yeah. That's the big one for sure.
Good on you for putting electric resistance water heaters. There's a lot of things happening in this world that are, not that an efficient use of electricity. Like in California, enormous amounts of indoor agriculture, enormous amounts. And it's like, so if we can grow cannabis indoors, then we can also have electric resistance water heaters if that helps save the world. Can we have a little perspective here?
Yeah, totally.
So thank you, Dylan. Thank you so much. So
absolutely,
folks, and head on over into the chat. People would like to, chat you up, so to speak.